Okay, so what do we do? First things first. Help us out here. What are we doing? Find the domain. Okay. Okay, so this is, yeah, we got something good going here. So we gotta find the domain. Where? Good. Okay, because we have a red flag here. We have stuff on the bottom of the fraction involving variables, right? So everything on the bottom, all this stuff, that stuff cannot equal 0, right?
Yeah.
Okay, so what is that stuff? Well, it's x squared minus 2. So if I add 2 to this side and square root, what do I get? X cannot equal plus or minus, right?
Yeah.
Okay. Everybody agree? Questions?
Why does it matter?
It definitely matters because those are going to be vertical asymptotes. Those are places. Those are the only x values excluded from the domain, but we got to have all of them. Okay.
Got it.
Make sense? Anybody want to see that algebra? Or are we good? Okay. Okay. So next step. Find the derivative. All right. So this is what's my rule? Quotient. Okay. So let's see here. Ellie, talk me through the quotient rule on this one. What am I going to get if I'm differentiating this?
X squared minus 2.
Good. Times.
2x.
Good.
And then plus. Minus.
Minus.
X squared plus 1. And then times 2x.
Okay.
All over x squared minus 2 squared.
Good. Right?
Wow.
Bottom square. Very good. So there's our derivative. We definitely want to simplify this, right? So if we distribute the 2x in both parts, what are we going to get? We're going to get 2x cubed minus 2x cubed, right? Everybody agree? So those are going to cancel.
Negative 6x.
And then I'm going to get, right, negative 4x minus 2x is negative 6x.
Whoa.
I got you.
Okay, because, here, I'll put the, because here's what we really get. We get 2x cubed minus 4x minus 2x cubed minus 2x. Okay? And then on the bottom, do we want to expand that? No. No point. Leave it. Exactly.
On y double prime?
You missed the squared on the x.
Did I?
On the bottom.
X squared minus 2 x squared.
Oh, yeah. Okay. Question?
Onward.
On y double prime, would it help to expand it?
No. You don't ever want to expand it. Right, you don't want it.
Probably don't expand it.
Okay, so let's go down. We'll leave some room to do some stuff with that derivative, find critical numbers, and let's move down to y double prime. Okay, that is what, how do I differentiate that one? Same, okay, quotient rule. Lucas, help us out. We've got to differentiate this. What am I going to get? Good. Good. Good.
Why negative?
Minus
Negative 6x.
times. Good. So we had a 2-layer chain rule there, right? Good. All divided by, good, the quantity x squared minus 2 to the 4th. So once again, we can do some stuff here. Okay, but this time let's talk about what to do. Now, we got some options, but we want to pick the good option. We could expand this all out. Good idea?
No.
Bad idea. We're going to look to factor it instead, right? Because we want it factored anyway. So do we see any like bases?
Negative 6 and x squared.
Okay, the -6, good, there's something we can factor out. And then we have an x squared minus 2 base that we can factor out, right?
Yeah.
Okay, and that's gonna make things a lot easier when we do it that way. So now we end up with -6, so those are gone, times, what power of the base x squared minus 2 can I factor out?
One.
To the 1, okay? And then I'm gonna have a bunch of leftover stuff. Well, what's gone? That's gone, that's gone, and the -6's are gone, right?
True.
So then I'm left with
X squared minus 2.
this, good, times, or minus,
Two.
Two.
so
4x.
4x.
Where?
Just
4x squared, good, because there's an x too, right? Can't forget him.
Okay.
So minus 4x squared,
Oh. 2 times 2.
2 times 2x.
Okay, thank you.
okay? So those three things combine to give me that, right? Okay. All over the bottom, yeah.
Why did you have so much space? Why did we only do that?
Why did I what?
Why didn't you?
Have so much space?
No, why? Why didn't you take the x squared minus 2 out of the bottom?
Oh, I can't. So, well, I can, what I'm gonna do is I'm gonna cancel a like factor, right? We took the x squared minus 2 out, and I could even maybe do this, and do this all in one line. But we can do this, can't we? We could go, that x squared minus 2
Yeah.
will cancel with one of those, right?
Yeah.
Okay?
Okay.
And so this does simplify quite a bit. Then we end up with -6, really just getting distributed through this thing now, right, and combining like terms. So we've got, what's in here? Well, I'm gonna get this is gonna give me, yeah, -3x squared minus 2 times -6 is, yeah, right? And you know, there's really no reason, I'll tell you what, why distribute the 6? I guess that doesn't make any sense, does it? That was kind of dumb. Why don't we just distribute the negative though? Right? If we just distribute the negative through, see what I'm saying?
Yeah.
Then we would just end up with my 6 out front, and this would just become a 3x squared plus 2, right? We might as well leave it factored. And then on the bottom, we've got an x squared minus 2 cubed, right? Okay, so let's let me pause there. Let you take that in.
And then you multiply this negative.
Where did the
Root.
3 go? Because you took it out, yeah?
Where did this 3 go?
No. I mean, it's not a 4 on the bottom anymore. You
No,
took
because I
one.
canceled the like factor.
Okay.
Yeah. Okay.
Thank you.
Mhm.
So there's
Say it again?
no critical
So there are no critical numbers, good.
numbers.
Well, we'll get to that. Let's do the first derivative first.
Why?
So what about right here?
Can you like take one step back for a second?
Go down here.
No, just that we can't see.
Oh, yeah, I got you. Okay.
How'd you get the top?
How'd I get that? Because all I did was I just distributed this -1. So I don't have a negative times a negative, right? Or I could have factored out a negative and see what I'm saying, multiplied it by that, either way you want to think about it.
Why do critical numbers?
Okay, on this one, because, well, let's talk about that now. So we already know that we have restrictions on the domain such that x cannot equal plus or minus the square root of 2. We've talked about this before, but when we have stuff like that going on, and it's a vertical asymptote, isn't it? Because those are values of x where the bottom equals 0 and the top does not, right?
Yep.
Okay, so those are vertical asymptotes. We know that if there are vertical asymptotes for a function, all the derivatives of the function will always inherit those, right? Does that make sense? So technically, I mean, we know we look for first derivative critical numbers wherever the first derivative is undefined or equal to 0, but it's undefined at the same place as the function is, so are those critical numbers?
No.
No, they're not, right? Critical numbers are only important if they're places where the function exists, and it doesn't exist there, right? So then we ask ourselves, are there any places where the derivative is equal to 0? So a fraction equals 0 when the top is 0. So where is the top 0? When x is 0. Okay, so we get a critical number. We get a first derivative critical number at x equals 0. Okay?
Yep.
Let's go down and look at the second derivative. Well, sure enough, the bottom is undefined or is equal to 0, so the fraction is undefined at the same places at the asymptotes. So those are not critical numbers. Is the top equal to 0 anywhere?
No.
It's not, and we can tell that by looking at it, right? Because if I were to try to set this factor equal to 0 and solve, when I solve for x squared, when I solve for x, I'm first going to subtract 2, so I'm getting a negative number. We already can see when I take a square root of a negative number, what's going to happen. I'm not going to get real results, am I?
Uh-oh.
Right? So when I solve this, I'm going to get imaginaries, and so there are no real numbers, or there are no critical numbers. Yeah, right?
But that's the second derivative. I thought that means there's no inverses.
That means there's no inflection points. Right, there's no places to even look for inflection points. They
Yeah.
don't
So
exist.
this is
Right.
pretty much a big.
No, I mean, it's a function, but now this is just a different kind of function. We still can sketch a graph of this, and that's what I want to show you. This is a kind that we haven't really done before. They're pretty easy to sketch, but you got to take advantage of the asymptotes. Okay, there's one other thing we haven't done yet, though, for this. If we go back up to this original function, let's try one more thing. So x squared plus 1 over x squared minus 2, right? Okay, what is the limit of my function?
Is this going on our notes or are you just asking?
No, this goes in your notes. This is important. As x approaches plus or minus infinity,
One.
what's it going to be?
1.
1, right? Because we know that this is the kind, these are now easy for us, right? This is 3-5 step. 3-5 step is simple. You can do this by inspection. We look at this and we know that the ratio of the leading coefficients, because I have the same powers of, the same order of polynomials, top and bottom. The highest powers of x are 2, top and bottom. So then we just look at the ratio of the leading coefficients, which is 1, right? And so this tells us then that both edges of this function, the tails of both ends, right, clear out to the left and clear out to the right, we have the asymptote y equals 1, right? So that's equal to 1, so we have a horizontal asymptote at y equals 1. Okay? So now let's put all this stuff in our table.
Uh-oh.
Alright.
So we had we can take a limit as we approach negative infinity. That's all negative numbers except for one of them are part of our domain. All positive numbers except one are part of our domain. Those two numbers were negative root 2, right? And positive root 2. And those were places, because remember, look at our domain, right? Those are the two values that are not allowed. That's where we get zeros bottom, but not top in our fraction. And so we can go down to this first row, the row for y, and y is undefined. There, right? So that tells us something really important. That tells us that what is this? Vertical asymptote. So VA, right? And we divide this thing up, right? Okay, what is the limit? Now this is really cool how we put this in our table. What did we say the limit of y was as x approaches plus or minus infinity? 1, yeah. So the limit goes there, right?
What?
because you can't ever get to negative infinity. What we're really doing is taking a limit. Maybe you want to even write limit up there. So you know, remind yourself that it's a limit, but that tells us something important. That tells us it's a horizontal asymptote, doesn't it? So over here on this edge, we might even write horizontal asymptote y equals 1.
What about 0?
Say it again.
What about 0? Do you not put it on there?
We might. Oh, that's our other critical number, isn't it? So yeah, we do, definitely. We just haven't added it yet.
Oh.
So our other critical number, we had one other one. That was at x equals 0, and that was a 0 of the first derivative, right?
Yes.
Okay, so thank you. Okay, so what do we know? We've got our second derivative factored right there, don't we? Right? So we can apply, we always want to work as low down in the table as we can because it gives us more information, right? So let's work down in this row. Let's use the second derivative test. What is the sign of the second derivative when x is 0? Positive times positive divided by
Negative.
negative. So what is it?
Negative.
Negative. Okay, so that's negative, which means that what do we have going on right there?
An inflection point.
It's a minimum, right? Because we have a 0 first derivative, meaning horizontal tangent, combined with downward concavity means a sad function, right?
Wait, yeah, that means
What is
the
it?
maximum.
Sorry, maximum. I said minimum. I always do something like that. Yeah, so it's right. So it's got to be like this, right? Right? Okay. While we're at it, let's just look, let's pick any test point we want to down here to the left of this asymptote and any test point to the right of this one. So how about like -10 and +10? And what are the signs of the second derivatives there? Well, the top's always positive, isn't it?
Yeah.
So the bottom is going to go as the sign of the bottom. When x squared is -10 or +10, what are we going to get? Positive. Yeah, so then that's telling us what about everything to the left of this vertical asymptote? Concave up, right? Okay, makes sense? Okay. So, okay. And over here it's concave up, right? That's enough information to sketch this whole thing. Let's go ahead and just, there's one point we need here, I guess. -1/2. Okay, because if we go back and plug it into the original function at 0, we get 1 over -2, so -1/2.
True.
Okay, so now that's all we need. Now we can take this table, we'll go to the next page, and we'll sketch it based on that.
Wait, is that positive? Especially under the 10.
Yeah, it's under the 10, yeah. Okay, there's our stuff. So, see what we got going. So this is 0. Let's make this 1, 2. Okay, so then we get at square root of 2, which is about right there, we're going to get vertical asymptote. Negative square root of 2 is about right there, vertical asymptote. Okay, let's tackle the middle first. If I only have one extremum in the whole thing and it's a maximum, what's the only way, if this part of the curve has to go through the point -1/2, what's the only way I can draw this thing?
Positively.
And it's got to stick to the asymptotes too, right? So it's going to be down here, it's going to stick to the asymptote, go through that point and stick to the asymptotes going down to infinity, right?
Yep.
That's it. That's what it looks like, for sure. How steep is it? I don't know. I don't care. That's the basic shape. Okay? What about over here? What's the only way that I could, in fact, we could maybe do one more thing here just to see, are there any zeros of this well, never mind, we don't even need to. What am I saying? We don't even need to. So we also know we have a horizontal asymptote at y equals 1,
Yeah.
right? So let's put that in. Horizontal asymptote at y equals 1 looks like this, right?
Wow, this is a tricky.
No, this is super simple now. What's the only way? Let's look to the right of this asymptote, right? So we're looking to at the right section of this function. What's the only conceivable way I could draw this thing with upward concavity sticking to those asymptotes?
Like
Yeah.
like an like
It's got to go like that, doesn't it? Has to, right? Okay, because there's really only two alternatives. We know that there are no critical numbers any place except right here. That was our extremum, so there are no peaks or valleys anywhere, right? So this thing can't be complicated. It can't do anything like that. There's only two possibilities. Either it's going to be there, or it's going to be there based on the asymptotes, right?
That's down.
That's down.
Right, but that's downward concavity.
But we have up.
We have up, so that's not it. I'm saying that's the only other possibility, but it doesn't fit.
So it's on the same side.
So it's
No,
not
it's on the other
possible.
side.
Oh, yeah, we haven't gotten over there yet. I'm just answering Clancy's question. She wants to know, how did we know it looked like
Could you
this?
draw it like on my paper?
Let's see.
Like that? Or no? Like that?
No, because that has no concavity. Well, that has no concavity,
Okay,
right? It has to turn.
okay, yeah.
You see what I'm saying? This thing the asymptotes are there for a reason. We know that if we pan out, this thing is going to have to stick to the asymptotes, right? That's what asymptotes do. Well, okay, here's how it's concavity. Okay, because remember that everybody watch this because this is a really important question. The question is, how do we know that's concavity? Because sometimes when you think of concavity, you think of a bowl and it never turns up, but that's not it. Remember, all concavity means is that if it's a positive concavity, tangent lines sit where relative to the curve? Below the curve. So if I draw any tangent line here, it doesn't matter where, in this region right here, when I draw a tangent line, they always sit below the curve. See what I'm saying? Okay? So what about over here then? If I have the same kind of thing, I've got these red asymptotes, and it has to be upward concavity, so the tangent lines sit below the curve. What's it going to look like over here? Yeah, it's the mirror image. Okay? Good.
Reflection.
Yeah. Right? Okay, makes sense?
Yeah.
Okay, there's something else going on here that's really important too.
Okay, so I don't see it now.
Would you notice, what's that?
I don't see.
Looks like an
I
inner.
don't see it.
Okay, so do you notice anything about this function? Do you notice any symmetry?
Yes.
Right down the middle, that'd be bilateral.
Good, it has bilateral symmetry, or folding symmetry
We have to run the bias.
about the y-axis, right? That's important. So if we go back and look at the original function, I want you to see something here. This is going to bring together some things we talked about a couple of years ago, you probably talked about last year, and now you can kind of see it in a calculus sense, and it's good stuff. So look at this function, and let's quickly review how we check for symmetry. Because this is also a great hint when you're doing these problems. This is a good shortcut sometimes. Okay, when we look for symmetry, when we're graphing functions or relations in general, when we look for symmetry, there are two kinds of symmetry that we really look for. If we're talking about functions, we don't really care if we can fold things vertically, right? That's not really important to us. Because if it's a function, and you understand what I mean by that. Look at a shape, a highly symmetrical shape like a circle.
So
If we look at a circle, the circle has every kind of imaginable Euclidean geometric symmetry, right? We can fold it. I could fold it on this line. It overlaps with itself, right? If I fold it on this line, it overlaps with itself, right? Or I can spin it around the origin and it overlaps with itself, right? If I spin it through any rotation, it overlaps with itself, okay? But a circle is not a function, is it?
No.
It violates the vertical line test. So if I just take a function like maybe a semicircle, obviously if it's a function and it doesn't line up vertically, could it ever possibly have symmetry over the x-axis?
No.
No, it can't, right? It can't. So we don't really care about folding things over the x-axis when we're dealing with functions. All we care about is, can we fold them over the y-axis? And can we rotate them? Okay, see what I'm saying? So if we look at some other kinds of functions here, you tell me real quick. Think of a function that has reflective symmetry over the y-axis. Parabola, y equals x squared. Okay, so there's one that does. So that's y equals x squared. That has folding symmetry, right? Okay, think of a function that has rotational symmetry about the origin. What I mean by that is if I put a tack in it and I spin it 180 degrees and stop it, will it line up with itself? X cubed. There you go. How about that? Now I knew you were going to say those ones, and those work out perfect. Okay. So this one, y equals x cubed, has rotational symmetry. Okay. What do you suppose we mean by even symmetry? When we talk about even symmetry in math, even symmetry refers to folding symmetry over about the y-axis, right? Why do we call it even symmetry? Because a polynomial with even exponents is going to have even symmetry. Doesn't work for trig functions, but we deal with polynomials a lot, and that's where it gets the nickname an even function, because it has even symmetry. Where do we get odd symmetry? A polynomial with only odd exponents will always have, it might look complicated, but it's always going to have rotational symmetry about the origin, right? So hence the even and the odd. All right, so how do we test for these symmetries? Well, for polynomials, you can just inspect them. It's easy, right? Even and odd is very helpful to us. Those names remind us, and real quick, just remind me, you tell me, not by graphing it, but just by looking at this polynomial, I want you to tell me what kind of symmetry does it have? Okay, it's odd symmetry, right?
Odd.
Okay, what about
Is that a 6?
that's a 6.
Even symmetry.
Okay, it's even because all the exponents are even, but what's the exponent of that one?
Nothing. 0.
It's 0, because there's an invisible x to the 0 there, right?
Yes.
What's x to the 0?
1.
1. Okay, so that's even, isn't it?
Yes.
Okay. How about this? Neither. Because it has parts that are even and parts that are odd, and so it screws it all up. Okay.
So it's all wacky.
So it would be wacky, yeah. Okay, how about this one? What if we do let's see. Okay, I'm trying to think here, so if we get okay. Okay, we have a second here. I want you to see if you can find this pattern. I'm going to pull up a graph. Just watch this real quick. Tell me what I'm going to get.
Okay.
Even.
Sorry about that. That's the screen, right? I think. Yeah, good. Okay, yeah, look at that one, right? So that's the function. Is that the one we just did?
No, that's what we did
A while ago. But it's what's going to be? What do you think is going to be the symmetry of that one, if anything?
It's going to be even.
Okay, let's graph it and see. Sure enough. Okay. Let's try another one. I want you to see if you can see what's going on with this. What if I make this top one cubed?
It's gonna be wacky.
Oops. Cubed. What happened to my...
No, it's gonna be.
What the heck happened to my calculator? It definitely is.
It's being
The
wacky.
graph button.
Where's the graph? I can't see any button.
There's enter though.
Just go up, go down to the right.
So
You got it,
like
you
right
got it,
there?
Right there. Look,
Oh, I got it.
hey, got it back. We don't need the whole thing.
Okay, what happened?
So the bigger exponent takes.
Oh.
No.
There.
Oh, it's that second one.
Oh, I put a I put a comma in there. Okay. Okay, so I gotta
Delete.
delete.
Oh no, this is gonna not be good.
How am I gonna find
Okay,
delete
so,
though?
alright, we go down a little bit. Oh. This is way more fun than
Maybe try to put on the keyboard like
Right
this.
there.
Yeah.
Hey, how about that? Okay, good, right? So now, once again, graph was right there. Okay.
So is it gonna take the?
Rotation.
Okay.
So it's gonna take the higher exponent.
You missed some life changing stuff.
So now let's go down and make this on the bottom. Watch what I'm gonna do. So now notice the pattern. Listen, please. So that one was, first one was even over even, right? Rational function. This one was odd over even. Okay. I'm gonna do odd over odd. Watch what happens.
It's gonna be, yeah.
It's gonna be.
Oh, I gotta find x. Where the heck's that?
It's pretty up top.
Yeah, it's by the thing.
Oh, darn it.
Go down.
Go down.
Oh my gosh, I gotta look at a calculator.
Go one down.
Where's quit?
Oh, that'll be
Go,
down.
go below it.
Oh, so I gotta go second now. So it's like second. There we go. So it's right below that, right there.
Right here, right there. Quick. Yes.
Oh, you're not in y equals anymore.
You know why you-
That's okay.
Chili beans.
You can get it though.
You just click all the buttons so you can get them back.
Oh yeah, you can try minimizing.
Okay.
Or just shut down your
Just restart it. Lucas.
Yeah, you'd like that, wouldn't you?
Yeah.
We'll just trick the bug, just restart it.
There we go. How about that?
Like I said.
Okay, so now we're gonna make that an x on the bottom. Make that an x. And let's go up and make that like a fifth, how about? Okay, and let's graph. Watch this one. If I'm thinking about this right, yeah. Okay,
What was that? I just want to be the odd one out.
what's the rule?
You're just like you're subtracting it. Like
Same.
five minus.
Yeah.
Okay, shh, Ryan's got the floor. Listen, please.
You have the exponent of 5 minus the exponent of 3, so you get 2, which is an even one. So you have that.
Okay, well, no, that's not it. What's going on here is the sign.
Both even. They're both even.
Okay, what's going on is it's the sign of the polynomial on the top versus, by sign I mean it's the symmetry of the polynomial on the top versus the bottom. If they were both even, the rational function was even. If they were both odd, the rational function was even. But if they were mixed, it was odd.
Well,
It's like plus the
That's
same
just
thing.
like
plus your
adding
any numbers. Even plus even
So
is
you
even.
just like.
Okay.
Even plus odd is odd. Odd plus odd is even.
You don't mean plus though, you mean times. Right? So they're like
It's like
sign
positives
rules, aren't
and
they?
negatives.
They're like sign rules for products.
Yes.
I don't mean time.
Right, so an odd is like, well, an odd is like a negative sign, right?
Yeah.
And an even is like a positive sign. And so, see what I'm saying?
Two negatives.
Right, you get it though?
Yeah, I get it.
Okay.
7 plus 7 is a
So then you should be able to look at rational functions. Hey, there's too much talking, I just can't, you guys are, hold on, I know they're good questions, but hang on, let me kind of summarize this for you, because this is, I don't think everybody's getting too confusing. If you've got, polynomials are dead simple. Polynomials, you're just saying if they're all even exponents, it's even. If they're all odd, it's odd. If they're mixed, all bets are off. If it's a rational function, that means a ratio of polynomials. So polynomial in the numerator, polynomial in the denominator. Once again, and if there's any mixed symmetry in the top or the bottom. Like if the top is a polynomial that doesn't have even or odd symmetry, who cares? Everything's broken. But if the top polynomial is all even and the bottom is all even, then it's even. If the top is all odd and the bottom is all odd, it's even. If they're mixed, top is all even, bottom is all odd, or vice versa, it's odd. That's pretty cool. I mean, that saves a lot of time, right? So you can look at this and you can know what the symmetry is going to be. And what are the ramifications of that? Well, I didn't really have to do this whole thing, did I? Really, all I had to do, if we go back to this problem we were working on, where's the graph? Right there. I only had to do half of it, didn't I? Right? Because I knew this was going to have even symmetry. So once I did this half, it was pretty easy to begin with, but what if it weren't? What if this had been complicated on this side? Then all I'd have to do is say, well, I know this is just going to get reflected over there, so I'm done. Right? See, that's a space or time saver.
So you don't have to do once.
So what?
No, I'm thinking
You
about
don't have to plug in one side.
Yeah, you would.
Yeah.
You'd only have to do, right, you'd only have to do one thing. And if I knew it was odd symmetry, I also could have stopped. I could have said, okay, well, whatever I got over here, if I spin it 180 degrees, I'm going to get what's over there, right? So in general, that works for polynomials and rational functions. Just real quick, let's remind ourselves, what is the test for even symmetry and odd symmetry? This is just so. Even symmetry test, and it's always this. You're always going to say, what's going to happen if I evaluate the function at the opposite of x? What's going to happen? Well, think even symmetry, right? Even symmetry was symmetry like this. So when I went out to positive x, I got back a certain y value, a certain value of the function. If I go back to negative x, what am I going to get? Same value. So it's equal to f of x, right? Okay, odd symmetry. The odd test, well, think about the picture. Odd symmetry was like this. So if I went out positive x, I went up to positive y. What are the coordinates going to be right there? Negative x, negative y. So what's the answer going to be?
Negative x.
Right? So those are the tests. If I plug in a negative x into my function and simplify, and I get back the very same thing I'd get for a positive x, it's even symmetry. Even if it's a weird function, like a trig function or something, right? Same thing over here. Okay? Make sense? Okay.
Will you leave that up for just a moment?
Yes, I will.
Sorry. 3 minutes.
So you guys, I gotta take roll. So do you kind of see what I meant at the beginning of the year when I said in calculus you will do more algebra than you've cumulatively done for your entire careers? I mean, it's just everything kind of comes together in calculus. It's a great review for every math class you've ever taken in a way because it all comes together in this one class.